was on mute. All right. So I'll be talking a little bit about Tegra and my and some other people's efforts to try to understand its internal workings, or rather the workings of the user space drivers. So first I'll tell a little bit about who I am. I have about 20 years of graphics programming experience. 10 of those years have been professionally. I used to work at ARM and Phalanx at the Mali driver team, making the drivers that Luke here has been so friendly to try to pick apart. And while doing that, I was involved in the development of the OpenGLES 1.1 and 2.0 standards. I'm a reasonably active open source contributor. My biggest portion of that is for Git, but also the casual patches to some other projects. And I'm an active demo scener, if anyone knows what that is. Unfortunately, no, because they don't. There's a lot of demos for ARM. Oh, I have released lots of demos for ARM. I used to work at ARM.
Can you close your jacket?
Yeah.
Ah,
sorry. All right. So this is titled Grate, so I'll tell you a little bit about what Grate is. It's an anagram for Tegra, as you probably didn't see, but it's an effort to reverse engineer the GPU and eventually to create an open source driver from it. It's probably the furthest behind of all of these ARM SOC projects due to not very much time available for doing this. But yeah, we'll still give it a go. Yeah, and the usual, everything here is based on reverse engineering, so don't invest all your life savings into something based on something I'm telling you here. It's most information might indeed be incorrect. So I'll tell a little bit about what has happened so far. Yeah, so in the fall of 2012, I heard about the Lima project and I joined their IRC channel, but it was so boring because I'm NDA tainted due to my ARM work, so I can't touch their stuff. So instead I decided, or rather Luke convinced me to start looking into the Tegra. And then, so I just quietly hacked away, and around FOSDEM last year I had implemented command stream capturing and parsing, so I can pick it apart and see a bit of what's happening. I did some NVTools shader database or register database for some of the. I'd say this has most of the OpenGLES non-shader state, but it's a bit difficult because a lot of this gets compiled into the shaders as well. I had a very rough fragment shader disassembler, yeah, and I had reverse engineered the proprietary compiler shared object interface, so I could compile shaders from my own programs without using their driver. And then I got bored with it and kind of stopped working for a while. So at that point, or a few months, I think a month later or so, I was told by Luke that I had to get my ass onto IRC because someone was doing something, and that was Thierry. And it turned out he had not at all been idling while I was procrastinating. So he had already, I think, been working on the Linux kernel drivers. He started hacking together some libdrm interface for that. He replayed command streams, and he started on a DDX driver, and he even did some work on Gallium, so for Mesa. And then, yeah, Thierry got hired by NVIDIA. So I'm slowly trying to kind of follow up on what he's doing, but bear in mind that my biggest interest here is the reverse engineering part and not so much the driver development part, because I've already itched that scratch at ARM. So, yeah. But I will, you know, give it a go. But yeah, awesome work, Terry, and more awesome work in the future. He's the one in the green T-shirt in the back there. Yeah, and also I should mention that Rob Clark, who's doing the Freedreno project, he has also had a little bit of luck at some of the stuff, so helped out a little bit as well. So yeah, the current status as of now. So this was, you know, a year ago. So yeah, I've basically been focusing on the Tegra 2. Tegra 3 and 4 I will mention a little bit about, but it's yeah. So we have command stream dumping. We can replay that and do some basic rendering. Been tampering with a lot of state to kind of confirm suspicions, stuff like that. So we can do, you know, a little bit of stuff there. Yeah, there's an upstream Linux DRM driver, and now it's even, as of I think 2-3 weeks ago or so, it has support for the 3D core. Downstream libdrm support. The blue things there are links in the in the slides, but I'll put them up online if someone wants to have links. Yeah, now we have a very unfinished Mesa Gallium driver and can only do GL clear and read pixels, but yeah, it's at least some basic stuff working. So it deals with, you know, tiling and these kinds of things. So yeah. So Tegra 3 seems to just work. I don't really know this, but I haven't seen any real differences in the command stream, so it looks like it's just the same 3D core. Tegra 4 has some more registers that we've found. Some of I don't think it's strictly compatible, as in I think the first command streams we didn't replay there, but there has been replayed some command streams on Tegra 4 hardware. So it seems to be roughly compatible. K1, you heard about, those of you who were in the previous talk probably heard a little bit about that. It's Kepler based. It only has the GPU or the 3D core from the Kepler. Rest of the GeForce infrastructure seems to be lacking there. So I have not done any work because yeah, I'm focusing on the 3D core on the Tegra. So that's the one that's being replaced. And yeah, this is something Nouveau will have to deal with, I guess. What? Let's discuss that later, okay? I need to work with you guys on some things. Yeah, so I won't talk anything more about the K1 in this talk. This is just a short summary. All right, so it says demo, but apparently we can't. Yeah, I'm not so good at reading emails, so I missed the detail that I can't connect HDMI equipment to the big screen. And my demo platform doesn't have an external monitor, so yeah, I can't show you anything here either. Yeah, but so I don't have a screen to show it on either. So yeah, it's a trim slice, a screenless device. So I'm sorry about that. It wouldn't have been too exciting. It's just like a rotating triangle with the growth shading. So it rotates quickly though. Yeah. So imagine a triangle rotating here, I guess. Yeah. So I'll go a little bit into the hardware here. So a short overview of the GPU is it's codename AR20 from NVIDIA. This is deeply found some traces about that deeply down in some code and stuff like that. It's an immediate mode renderer. It consists of at least 3 components. The graphics 2D, 3D core, and then there's also some kind of video system. Encoder or decoder. I don't really know the specs of that. Yeah, the clients are programmed, these components are programmed through something called host1x, which is a DMA engine for writing registers to the GPU, so drives the GPU. And it has a proprietary OpenGL driver, which is useful for reverse engineering. Yeah, so the GR2D it's publicly documented. Great. So this means that everything that needs to be doing a DDX driver, for instance, is available. Yeah, you need to sign up and agree to an end user license agreement, but it's not a very strict one. They have source code available for doing some blitz stuff like that. It can do a lot of different things, really. Blitz fills with tiling patterns. It can do tiling or linearly addressed sources or surfaces. It can do stretching, rotating, flipping, but only like 90, so multiples of 90 degrees rotation. Some kind of blending, and coverage sampling, anti-aliasing, resolve, which is quite interesting, I think. It can do ROP3, yeah, lots more. So it can do basically. It's capable of doing all of the 2D operations from OpenGL, so it can do full blending and both with stencil masking and with scissoring and all of these things. So yeah, it's quite capable. Yeah, the GR3D is yeah, a bit different. It's a non-unified shader, so that it has a separate vertex and shader and vertex and fragment shader ISA. And yeah, it performs blending in the fragment shader rather than fixed function circuits, which means that we need to recompile the shaders all the time. It only has a 16-bit depth buffer, but it seems Tegra 4 added support for 24 bits as well. It has 16 render targets, including depth and stencil, which is quite a lot. But yeah. It supports occlusion queries, quite a bit of texturing features, although they do have some kind of non-power of 2 textures, which is not so nice, or rather, it only supports. Well, it supports without MIP maps, but also with MIP maps. But then, if you try to access outside of the 0-1 range, then you get an undefined result. So yeah, there's a separate extension for that one. Yeah, the standard derivatives, and a quite interesting, I think, draw path extension, which is for drawing 2D graphics, Bezier curves and things like that. I haven't really digged into that, but it's an interesting feature. So it might be that this feature is software only from the driver. All right, there's a video codec, but I haven't worked on it. I'm not a video expert, so I'm not gonna try that either. If anyone wants to have a look at it, feel free to. All right, so the vertex shader instruction set is basically a subset of the NV30, which is means that it can do 4-component vectors for normal ALU instructions, or single-component scalar SFU instructions, and it seems to be able to do those in parallel. Although I don't think I've ever seen the compiler generate that. It has no control flow, so all loops needs to be unrolled. But it's very straightforward to generate code for. It looks basically exactly like TGSI. So yeah. And there's already a backend in Nouveau's Mesa driver, so probably can share some code there. Yeah, the fragment shader ISA is quite a bit more interesting / crazy. So all the registers are either representing one 20-bit floating point value or two 10-bit fixed point values. That's 2.8 fixed point signed. There are at least 3 separate instruction streams. So there's the shader programs are not one stream of instructions. There's 3 different, at least. I suspect there's 5, but I haven't really figured out all the details. Streams, and there are some additional control streams that kind of define how they get executed or scheduled with each other. So there's the ALU stream, the arithmetic logic unit, and there's the multifunction unit, which does both varying interpolation and complex function evaluation. So it does typically, interpolate varyings over the triangle, or do sine, cosine, these kinds of things. And it seems that those two are not executed in the same clock, so the instruction word has room for encoding both kinds of instructions in the same kind of word, and yeah, it seems they are executing it at 2 different clocks. There's a texturing unit, and then there seems to be some kind of export unit for writing the color to the color buffer. And there's some once I start doing shader that spill registers and stuff like that, then even more stuff starts to show up. But I haven't really understood that part yet. And again, there's no control flow whatsoever, so all loops unrolled. Yeah, all conditionals become either conditional selector or predicates. So the ALU unit, it's pretty well understood. There's only like a few bits that aren't. There are only a few bits that I see pop up that I don't yet feel I have a good understanding of what it means. The instructions come in packets of 4 64-bit words, which either are 4 scalar operations or 3 scalar operations and up to 4 embedded constants. So that's either either 2 20-bit floats or 4 6 10-bit fixed point values. And yeah, the rest of it is basically a glorified MAD, and you can do it has 1 destination, 3 source operands. And this is an example for this is the MAD instruction. It has some bits to choose some of the different modes where it squares the C component before doing it, or it changes the order of adding, so it can multiply before it adds, and these kinds of things, or add before it multiplies. And it also has a bit that seems to mean that it accumulates the result, so the destination register just kind of adds to it. And when it does that, it uses some kind of special accumulation register, it seems. And it also has min, max, and conditional select. And I think, so my understanding so far is that if you change the MAD to min, you still get the C stuff. So it still tries to add C. So it's quite, You just pass 0 in for C instead, so it's no problem. Yeah, and all the ALU instructions have predicate bits, so so there's some condition register that gets set, and it can execute conditionally based on that. Yeah, the results can saturate, the source operands can absolute or negate bits for that. Seems I have some more under here, but I can't see it. Yeah. The multifunction unit is probably based on this paper called a high-performance area-efficient multifunction interpolator, which is an NVIDIA research paper, and it proposes the idea of merging the varying and the complex function evaluator to one unit. So the complex function evaluator part is pretty much understood. It's very simple. It just takes a register and and it writes the destination of the result to the same register as the source, and it does these operations. In typical NVIDIA style, there's two-step trig and also the exponential function. So I haven't studied what the intermediate result is, but it doesn't seem to require any extra values or anything like that. So it might be range reduction or something like that. Yeah, but the varying right is still a mystery. I see which varying it interpolates in each instruction, but I can't figure out which register it writes to. And I've had some friends look at this. Rob Clark also had a look at it, and we still haven't been able to figure it out. It's a mystery. So yeah, if someone else wants to have a look, then that would be awesome. Yeah, the texturing instruction is somewhat understood. It seems the encoding is really simple. It's not entirely clear how it passes the texture coordinates. That's not so much that it's a mystery, but more that I haven't really felt like working too much on that without getting the varyings working, because looking up the same texture coordinate for an entire triangle is extremely little interesting. It's boring. Yeah, but it seems simple. Both lookups of 2D and cube maps compiles down to the exact same binary code. So it seems the hardware deals with all the stuff really. So yeah, there's no need to, for instance, normalize the cube map inputs as some ISAs require. Yeah. And then there's the export instruction that I found which random target it writes to, but the rest just looks like garbage to me so far. So I'm not really up to speed on that either. Yeah. So as you guys probably understand, this is rough stuff, and the help is definitely wanted. There's some things that needs to be done. Some of this is just implementation work, and another is reverse engineering. So we have a bunch of libdrm patches that should be upstreamed, and yeah, finishing out the kind of the details. We should probably have an X or DDX driver finished. There is a stub driver, but it doesn't do anything with except from mode setting, I guess. So it doesn't accelerate any of the drawing. Yeah, and so that's, since the GR20 is, or 2D is pretty much documented, it should be pretty easy to do also. And we have a working libdrm interface, so it's mostly kind of knowing really how the DDX interface works, I think, which is the biggest path. I don't know the DDX stuff at all, so for me it would be quite a bit of reading code to understand what needs to be done. Yeah, and then there's the reverse engineering. The varying rights are, as I said, still a mystery. The fragment shader exporting, and then there's register spilling, which happens if you use a lot of registers, and they also seem to trigger the same kind of code path if you use more than 32 uniforms, because there's only the normal uniform upload code path. And there's some weird stuff there. I don't really see where the extra uniforms get sent to the hardware at all, but it does work. It does give the right result. So so it's a little bit strange. So maybe there's something wrong with my command stream stuff here. Maybe, yeah. Yeah, and there's the Mesa Gallium driver, and that's a huge piece of work, and it's probably going to go on for years. So yeah, that's pretty much my talk. If there's any questions.
There we go. How does the old NVIDIA stuff, which Nouveau drives, the desktop stuff, Tegra and Kepler, how do they all relate? If you don't mind me asking.
It's independent technology. It's a different thing. No
Te-
relation.
Tegra is apart from the vertex shader being NV30 basically.
The vertex shader is based on the OpenGL ISA, so it's
Yeah, but even the bit fields are exactly the same.
Oh.
Yeah, so it's the instruction, and I'm pretty sure they're just bolted on that kind of vertex shader strip.
And was the desktop technology not related to Tegra?
yeah. Well, the new Tegra, the K1 is just Kepler, but it has nothing to do with the old Tegra.
Yeah, I should probably start using AR20 rather than Tegra, because it's Tegra is a product line and not a GPU line.
Damn marketing people.
Yeah.
I'll admit I haven't been keeping up to date with what NVIDIA does and does not release. I think on the Nouveau side, they started to slowly share or start to work with the community. I thought I was under the impression that I was reading that Tegra was more open source than any of the other work that they have done so far. So the GPU bit is the only thing that is not open sourced in their SoC.
So the Tegra has great support in the kernel. The kernel work is they do excellent work and support.
So it's purely
more or
user
less
space that
everything.
is missing right now.
User space is missing, and I'm talking a bit to some NVIDIA people, and they're trying to get some agreement to get some information out, but I don't think there's any chance that they will open up their drivers or the documentations.
Okay, thank you.
Any other questions?
Yeah, you said the most enjoyable part of the project for you was the reverse engineering part of working on the chips. Could you just go through your workflow and the tools you use for that part of the project?
Sure. Yeah. I should have spoken a bit about that, I guess. We have a bunch of tools. Not anywhere as sophisticated as the Nouveau stuff or anything like that, but we do have a repository called Grate on GitHub under the what's it called, organization Grate-driver. That contains some library to hook into OpenGL programs, so you can LD preload, and it will dump out the command streams that are sent to the kernel. Besides from that, we have a disassembler for the vertex and fragment shaders. So that actually takes GLSL source code, compiles it with the on-target compiler, and dumps out the disassembly afterwards. Like, the compiler is a bit crazy because or not crazy, but untraditional in the way that its output, its binary, is actually a command list that you submit to hardware or to the kernel space. So it's not just the instruction streams. You actually get the whole thing to output. Yeah, there's some other. I have integrated some stuff with NV tools. I have some documentation for registers there. I'm planning to send that upstreams at some point, because I've also added some functionality to NV tools. For instance, reading 20 bits floating point.
Yeah, I saw that.
Yeah. So yeah, I think that's pretty much it for the tooling. Terry, do you remember anything important? No. Yeah. So and the workflow is basically writing small OpenGLES programs and looking at what they're doing, what the output is, how it changes when I change the sequence of commands.
Hi. Could you go into a slight bit more details of what exactly the upstreaming process looks like? Like, for instance, this XORG DDX driver that you have on the to-do list. Is that the XF86 video OpenTegra from Thierry that's been like dormant for over a year, or
Yeah.
is development happening in other places now, or?
Yeah, so there's nothing has happened on the DDX driver since Terry's work, or since he got hired by NVIDIA, I guess, and stuff like that. There has been a little bit talk from NVIDIA about the possibility of open sourcing their existing Tegra driver. So that might happen, but yeah, I wouldn't have my hopes too high for that either. Yeah.
And what about libdrm? How does that relate to like the GitHub Grate project?
Yeah, so there's currently two different libdrms for Tegra. One that is maintained by someone at NVIDIA for the kernel, for testing the kernel, and then there's another one which is maintained by another guy at NVIDIA or other Thierry. Now I think I'm the one doing the most things, most on that now. So there's the one under the Grate project, which I think is a cleaner approach to it. And the other one has a high-level API that is a little bit too high level, I think, on top of it. So yeah, I have some in there in the repository. There's some tests for doing some blitz and stuff like that with a 2D unit. So yeah, some functions for injecting the right stuff. So I think the DDX stuff, for someone who knows the driver, should be fairly easy, or I mean, to the extent where writing any software is easy. It's yeah, it's all known problems really.
And is that process like waiting on certain design decisions that are in fact waiting on the reverse engineering of some of these open issues to complete, or is that something where people can actually help out, or where you already have like a time frame of when you're going to be done or when it might be available?
No. There's no kind of project management at all. There's just some repos and some code, and yeah. So if someone wants to pick something up, then they're free to do that. I would appreciate if they let me know that they're working on it, so I'm not spending time on something. But apart from that, yeah, there's basically me and yeah, there's basically just me doing something right now. Yeah. All right, that seems to be it. Thank you.